Hi everyone, welcome to our live group tutorial today. We have a physics session planned today on series and parallel circuits. This session will be led by one of our tutors, Prashela, who is a student at Loughborough University studying physics. And she has 4 years of tutoring experience, so she's one of our best tutors, and she'll be leading the session today. So what she'll be covering is, as I mentioned earlier, series and parallel circuits, which she'll go through for the first sort of 45 minutes, running through the content with you, and then she'll be taking some questions at the end for the last 15 minutes. So I'm just going to hand over to Prashela now, who will lead the session. Prashela, please can you share your screen again? I think we lost it.
Oh yeah, sure, sorry.
Great, thank you.
Okay, hopefully people can hear me. Okay, so as Frederica mentioned, today we're going to be talking about series and parallel circuits. So you might have covered it at school already, but just a reminder of the equation that kind of governs all of electricity. So it's called Ohm's law, and it's V equals IR. And if you remember, V is potential difference. Sometimes you might hear it called voltage, but we tend not to use that one. Potential difference is what we want to use, really. I is current and R is resistance, where potential difference will be measured in volts, current is measured in amps, and resistance is measured in ohms. So that's just a quick reminder of the equation. Okay, so we'll start with parallel circuits. So this here is an example of a parallel circuit, and we know that it's a parallel circuit because it's kind of got this two-loop system going on. So that's how we know it's a parallel circuit. Now, the rules for a parallel circuit are really important to remember, and once you know the rules, it makes calculating currents and voltages and resistances much easier. So the potential difference across each component is the same. So that means that the potential difference coming from the battery or the cell is the same in this branch and the same in this branch. The total current through the whole circuit is the sum of the currents through the separate components. So what that means is that we have a current coming from the battery or the cell, and it splits into a current in the first branch and a current in the second branch. And with the equation that governs current in parallel circuits is that total current, so IT, is I1, so the current through branch 1, plus I2, which is the current through branch 2. The total resistance of two resistors is less than the resistance of the smallest individual resistor. So this one's a little bit more confusing, but what it is that the total resistance in a parallel circuit is less than the resistance of an individual resistor. And you'll see that covered a bit later on. But in the AQA exam board and for a lot of other examples in physics, you don't actually have to calculate resistance in parallel, which is quite good. Okay, so we'll move on to series circuits now. This is a series circuit, and you can see it looks a bit different to parallel circuits because it's only got one loop. It's only got this one loop. It's not got that kind of branch effect that we had in parallel. So series circuits have completely different rules to parallel. So what that means is there is the same current through each component. So the current total, so the current coming from the battery or the cell, is the same in this component, is the same in this component. So we only have one current flowing through the series circuit, and it's the same current in each component that is in our circuit. However many components we have, whether they be resistors, bulbs, switches, it's the same current throughout the whole circuit. The total potential difference of the power supply is shared between the components. So you can kind of see the differences now with parallel and series. So parallel, we have the same voltage in each component. In series, the voltage is shared. So we have this total voltage coming from the battery, which then splits into the voltage in the resistor and the voltage in this resistor. So you can see the equation is V total equals V1 plus V2. The total resistance of two components is the sum of the resistance of each component. So this is a nice little rule because it doesn't take too much maths to work out. So we have a resistance in this resistor and we have a resistance in this resistor. Now, the total resistance of this circuit is just the resistance of resistor 1 plus the resistance of resistor 2, which you can see in this equation here. So we're going to move on to our first question now. So I'm going to give you 30 seconds to have a little go at this question. A quick hint is that the first thing we need to work out is the total resistance in the circuit. Note that this is a series circuit, so the resistance of this resistor just adds with the resistance of this resistor, and then we need to remember to use V equals IR. Okay, so it looks like a few of you have started to work that out, which is really great. So the total resistance is 30 ohms. We just add the resistance of resistor 1, which is 20, and the resistance of resistor 2, which is 10. So 20 plus 10 is 30. So our total resistance is 30 ohms. And then we have that our current is 0.4 amps. So using V equals I times R, we know that V equals 0.4 times 30. So V equals 12. So if you got 12, well done, you were correct. If you didn't, have a look at the working and try to see where you might have gone slightly wrong. Okay, so we'll move on to the next question now. We've got another circuit here. We've been given the current reading from an ammeter, and we've got two resistors here. What is the total resistance? I'll give you 20 seconds for this one. Okay, so we're getting a few answers in. The majority of them say 15, which is correct. Well done. So the resistors add 9 and 6 because this is a series circuit. Now, it's important not to get confused because this kind of looks like a parallel circuit. We've got that 2 branch thing going on, but this is actually a series circuit with a voltmeter placed in parallel to the resistors. Now, the reason that voltmeter is there is because we want to measure the voltage across those 2 resistors, okay? So you know that 9 plus 16 is 15 ohms, and we want to measure the voltage of those 2 resistors combined. Now, it's important to remember the rule about voltmeters, and hopefully you know that voltmeters are always placed in parallel with the components that we're trying to measure. So voltmeters are always placed in parallel with the components that we are trying to measure. Okay, now that's the rule for voltmeters, but what about the rule for ammeters? Well, ammeters are always placed in series with the component that we are trying to measure. So they are our 2 rules for ammeters and voltmeters. So ammeters are always placed in series. As you can see, we've got our ammeter here and it's placed in series with the components that we're trying to measure. The components that we're trying to measure, in this case, are resistors. And we place our voltmeter in parallel. So always placed in parallel with the component, okay? There's reasons for that. Voltmeters need to be placed in parallel so we don't short circuit the circuit, and the same for ammeters. So it's really important that that happens, and especially when you're doing labs in school, make sure you follow those rules, otherwise you will blow up your circuit. Okay, so we've got another reading here. So we've got another circuit here, and we want to calculate the reading on the voltmeter, given that the 3 resistors are identical, and the 3 resistors.
Hi, Prashayla. Just have a question for you.
Yeah.
Someone wants to know whether or not voltmeters have really high resistance.
Yeah, that's absolutely correct. Voltmeters do have really high resistance, and that's the reason why we need to place them in parallel so that we can decrease that resistance and we don't short circuit the circuit.
Great, thank you.
Cool, so calculate the reading on the voltmeter. We're getting a lot of answers coming in for 2 volts, which is great. So we've got 2 volts in this resistor. So hopefully everyone understands why, but if you don't, that means we can go over it again. So current in series is the same across all 3 resistors, but if we remember and we go back to the rules for series circuits, voltage is shared among the components. So voltage here is shared and voltage here is shared. So if we go back to our question, we know that voltage must be shared. Okay, we know that voltage must be shared, but how is it shared? Well, if the 3 resistors are identical, then the voltage must be shared equally between all 3 resistors. That means we must have 6 divided by 3 different components. And we know that 6 divided by 3 is 2. So you're absolutely correct. There'll be 2 volts in each resistor. So 2 volts, 2 volts, 2 volts. So if you've got 2 volts, well done. Okay, so we've got another question here. This one's a little bit more complex. So it's calculate the voltage through each bulb. So we have a cell of 12 volts powering the circuit. We've been told that the current is 2 amps, and we have a bulb of 5 ohms resistance and a bulb of 1 ohm resistance. Okay, so I'd like you to work out the voltage in bulb 1 and the voltage in bulb 2. I can see that some of you are already getting the answer, which is really good. Well done. I'm going to give you 30 more seconds to work out the answer. Okay, so hopefully you've been able to work it out. So yeah, we have a 12 volt voltage coming from our cell and a 2 amp current. So first things first, let's work out the total resistance. So because we have two resistors in series, we know that the total resistance is 6 ohms. Okay, now we want to find out the voltage through each bulb. So we can do V equals IR for each bulb. So remember, we're trying to find the voltage for each bulb. So we take the current, which we know is 2, and remember it's the same current through both components because we're in series, times the resistance, so 5. So that's the voltage for the first bulb. And then for the second bulb, we have 2 times 1, which is just voltage is 2 volts, and don't forget your units. Okay, so if you got 10 and 2, well done. 10 volts for bulb 1 and 2 volts for bulb 2. And we can sense check our answer by adding up the voltages. So if we add up the voltage for bulb 1 and the voltage for bulb 2, we get 10 plus 2, which is 12, so we know we've done it correctly. Great, so we'll move on to the next question now. Similar kind of question, but this time you're not given the current, okay? So the first step is to find out what the current is through the circuit. So I'm going to give you a minute for this one. So what is the current through the circuit? So the rectangles that you can see here are indeed circuit symbols for resistors. Okay, so we're seeing a few different answers coming through. So I'm just going to clear that up for you. So again, we use V equals IR. So we know that the voltage is 10 and we are trying to find the current, okay? So first of all, what is our total resistance? What is the total resistance in this circuit? Well, we have a series circuit, which means the resistances add, okay? So we add resistance 1 to resistance 2 to resistance 3. So total resistance is 20 plus 15, 20 plus 15 plus 10 ohms. Now, 20 plus 15 plus 10 ohms is 45 ohms. So I can see people putting 45 in the chat. So yeah, that would be the total resistance, but not the current, okay? So the total resistance is 45 ohms, and then we can use that in V equals IR. Now we know that 10 equals I times R, and now we can replace R with 45. So now we know that 10 equals I times 45. So we can divide both sides by 45 so that we get 10 divided by 45 equals I. And if you type in 10 divided by 45 onto the calculator, you should get 2 over 9. So 2 over 9 equals I. And then 2 over 9 as a recurring decimal, if you decided to put it in that form, is 0.222 recurring. So that would be our current, okay? So our current is 0.2 recurring amps. So if you got that, well done. And if you also got that the total resistance is 45 ohms, which is that little step we need to do in between, then well done. Okay. So now we're moving on to part B of the question, which is what is the voltage through each resistor? Now we know that the current through the series circuit is 0.2 amps, and you can take the current going forward in the question as 0.22. Try to work out the voltage through each resistor. So that's resistor 1, the 20 ohm one, resistor 2, the 15 ohm one, and resistor 3, the 10 ohm one. So I'm going to give you a minute to work that out because it's a little bit confusing. Okay, so hopefully you've all had a chance to work that through. So we'll just go through the answers. So again, we want to apply V equals IR to the circuit. So we're trying to find the voltage through one resistor. So we take the current in the circuit, remembering that current is the same for each component. So that will be 0.22 as we just worked out. And then we times it by the resistance. So for the first one, that would be 20 ohms. So V1 equals 0.22 times 20, which is 4.4. So that's V1 for resistor 1. And then V for resistor 2 is 0.22 times 15. So V2 is 0.22 times 15, which is 3.3. And V equals 0.22 times 10. So V3 equals 2.2. Okay, so hopefully you managed to get all three voltages for each resistor. Not forgetting your units. I always do that, oops. So remember they're in volts, 4.4 volts, 3.3 volts, and 2.2 volts. Okay, so remember, we can always sense check our answer by remembering the rule that voltages in series add to give the total voltage. So we know that voltage is 10 volts in the entire circuit. So if we add up the voltages of each resistor, we should get 4.4 plus 3.3 plus 2.2, which when you add them up is really close to 10. It's 9.9 volts, but remember we did use a rounded answer. Okay, so because we use 0.22 amps, which was a rounded answer, when you add them all up, you are going to get 9.9, and it is 0.1 off of 10 volts, which we should be getting, but don't worry, it's literally only because we used a rounded answer. And in an exam, you would try to use your recurring decimal going forward, okay? So in an exam, you want to use 0.22222222 recurring And you can do that by using the answer button on your calculator and then timesing it by 2 or storing it in memories. Okay, so we'll move on to the next question.
Before we move on, Prashayla,
Yep.
there's quite a few questions coming in with people having requests for covering certain parts of the tutorial at the end again. Just a note to say, don't worry guys, I'll make sure that at the end when we have the 15 minutes left for questions, we go back to the places that you were a bit confused with them, then Prashayla can hopefully help clarify some of that stuff. Thanks.
Okay, so all my questions have just gone. Okay, sorry guys, my I think the website's just crashed, so I'm gonna have to reload the PowerPoint. Just give me a second. Okay, great. So before I show you the answer, we have 2 circuits here. Now this one's not really a mathsy kind of question, it's more of a wordy question. So remember, you definitely will have both in the exam. Remember, electricity is not just about equations, not all V equals IR. Sometimes we need to talk about what will happen to the circuit in words, okay? So it's important to understand the physics behind series and parallel circuits. So in diagram 1, you can see that we have a series circuit with 2 bulbs. And in diagram 2, we have a parallel circuit with 2 bulbs. Now, they're pretty simple circuits, but the question asks, in diagram 1, how is the brightness of the first bulb affected? So this is the first bulb, when the second bulb is added. So you need to have a think about the rules, and we'll just go over them quickly to refresh. So remember, parallel circuits, same current, current is added to give the total current, but voltage is the same. And in series circuits, we have the same current going through all the components, but voltage is added. Okay, so go back to the question. I want to know what would happen to the brightness of the bulbs if we add in another bulb. So say you take the circuit with 1 bulb and then you disconnect it, put another bulb in, what happens to the brightness of the bulb, if anything? Remembering that current is the same, but voltage is shared. Okay, so when we add bulbs in series, the resistance is increased. Okay, so if we remember, resistances in series add together. Okay, so the resistance of bulb 1 adds with the resistance of bulb 2 to get a total resistance. So resistance is increased and therefore current is decreased by V equals IR. So this means that the brightness of the bulb will decrease and the potential difference is shared across the bulb. So if you said the bulb gets dimmer, then well done, that's correct. Now look to diagram 2. In a parallel circuit, like in diagram 2, how is the brightness of the first bulb affected when the second bulb is connected? And why does this happen? So I'll give you a minute to have a think about that question. What would happen if the brightness of the first bulb, what would happen to the brightness of the first bulb when we add in a second bulb?
Hi guys, it's not frozen. Priscilla's just given you some time to answer the question.
Okay, so hopefully you've been able to work it out. So again, it's using the rules of the circuit. So as I said, they really are the most important thing here. And so we know that in a parallel circuit, each branch has the same voltage or potential difference. So the current has another additional path to take. And the current's kind of a bit cheeky like that, because you have two different resistances, but it always wants to go in the one that has a lower resistance. So that's another thing about circuits. If you have two different resistances, a lower and a higher one, you can think of resistance like kind of a squeezing of the current. So it sucks out the current. A higher resistance makes the current really squeeze and lets less of it through. So it wants to go in the lower resistance branch so it doesn't have to get squeezed as much, basically. So that's another thing to remember about parallel circuits. But yeah, if you were to add in another bulb, then the brightness of the bulbs would still stay the same, because we have the same potential difference going through each bulb. Okay, so first answer is that the bulbs will dim, and the second answer is that the bulbs will be the same brightness. Okay, so same kind of question here, another kind of qualitative one, so a wordy kind of answer. So if we consider the following circuit and take away one of the cells, so the cells is up here, these are the cells, what would happen to the brightness of the lamps? What would happen to the brightness of the lamps, and why? Why would that happen? So you're all saying dimmer, which is great, but why dimmer? So we have three cells connected together here in series to make battery. And if you take away one of the cells, then I can see you're all getting great answers. The voltage is lessened, so there's less potential difference if we take away one of the cells. So let's say each cell is 2 volts, so 2 volts plus 2 volts plus 2 volts. So let's say this battery was 6 volts because of 3 cells joined together. Well, if you take away one cell, then it's going to reduce to 4 volts. Now, if we have a lesser voltage, we have less power, okay? So power, and therefore less brightness. So a quick little side note, you might remember the equation P equals IV. So this can be used in conjunction with V equals IR. And this is only for the higher exam board. P equals IV and V equals IR. Okay, so power, not potential difference, power equals I times V. Okay, so P is power, I is current, voltage is V, or potential difference. Okay, so sometimes we need to talk about power, so it's important to remember both equations, and they should be on your equation sheet, so don't worry too much. Okay, so you're absolutely right, the brightness of the lamps would dim. Now, if lamp number 3 were to burn out, or you unscrewed it or it burnt out, what would happen to the other lamps? So if lamp 3 was to break, what would happen to the other lamps? Would it not be as bright? Would nothing happen? Or would it all just completely break apart? What would happen? Give you a few seconds to think about that. Okay, so I can see a few of you saying that it would explode. It's not going to explode. Maybe the bulb that burnt out might have it might be a faulty bulb, but the whole circuit won't explode. Okay, cool. So I can see a few of you putting your answers in, that there would be no light, and that's absolutely right. If this bulb breaks, if this L3 bulb, lamp number 3, breaks, burns out, that makes a break in the circuit. And because it's a series circuit and current flows through the same through each bulb, if this one breaks, current can't go through anymore. So these are going to turn off and the whole circuit is broken. Okay, so if you think about fairy lights at Christmas, if they were to be wired in series, one faulty bulb could break the whole circuit. Yeah, so if you have one faulty fairy light, that breaks all of the fairy lights and the whole thing turns off. So it's not very practical in real life. So when we are wiring lighting systems, we tend to put them in parallel. And we tend to put them in parallel so that current still has a chance to go through a different branch of the circuit. In this one, the current has got no choice but to just completely stop because the circuit is now broken. The current can't still be flowing, okay? So it's definitely more practical to use bulbs in parallel than in series. Okay, so we've got a few quick fire questions here. There's no circuit diagrams, so you might need to draw the circuit diagrams yourself to help you. So I'll give you maybe 3-4 minutes to have a go at these questions. Let's just do the first 3 first. So just do these first 3. So here we're just talking about series circuits. Cool, so I can see a few of you getting 2000 ohms. For the first one, that's brilliant. We just add all 3 resistors. No need to work out current or potential difference for this one. It's just asking you what the resistance in the circuit would be. Number 2, we have 10 120 ohm resistors in series. So you have 10 times 120, which is 1,200 ohms. So hopefully you got 1,200 ohms for the second one. Okay, and then we have a string of 50 15 ohm Christmas tree lights that are connected in series. So as I said before, if one burns out, they all burn out. So calculate the total resistance in this series circuit of 50 15 ohm resistors. So we have 50 times 15 ohms, and 50 times 15 is 75. Oh, 750, not 75, sorry. 750 ohms. So hopefully you got 2,000, 1,200 and 750 ohms. Okay, so we'll try the next 2 questions now. So 2 100 ohm resistors are connected in series and they're connected to a 1.5 volt battery. This just means 1.5 volts DC battery. So DC is direct current, which is what we're dealing with right now. So what is the total current flowing in the circuit? So don't worry about this VDC, it just means 1.5 volts. So what would the total current flowing in the circuit be? And if you've had a go at that one, you can move on to the next one. So VDC just means the voltage. So the V means volts, and then DC means direct current. The 50 from here is from the question. So I've just seen someone ask where the 50 comes from. So a string of 50 15 ohm Christmas tree lights. So 50 times 15 ohms. Okay, so first things first, for this question, you've got two 100 ohm resistors. So we do the total resistance, which is 200 ohms. So total resistance is 200 ohms, and they are connected to a 1.5 volt battery. So we use V equals IR, where V equals 1.5. And you want to find current, so I times 200. Divide both sides by 200, and you should be getting 7.5 times 10 to the minus 3, or 0.0075. It's absolutely okay for you to leave your answer in standard form if that's what the calculator gives you, but if the question does ask for it for a certain amount of significant figures, then you obviously do need to do that. Okay, so for the next one, those 15 ohm resistors that we had in the lights, we want to calculate the total current. So we already know the total resistance is 750 ohms, and we have a 115 volt source. So again, V equals IR, we do 115 divide by 750, which is 0.15. VAC, don't worry about that for now. AC means alternating current, but we're not going through that now. So just pretend that it says DC. Okay, so I'll just explain again. The fourth question, we already know the total resistance. We worked it out over here, 50 times 15 ohms. So it's those same tree lights. So the total resistance is 750 ohms, and they are connected in series. So we can do voltage equals IR. Voltage is 115. I times R, which now our R changes to 750. So if we do current voltage divide by resistance, we get 0.153. So 0.153. Okay, so we won't go through the last three questions, but if you would like to have a go at them in your own time, then that's fine. But I think now we're going to have 15 minutes for questions. So Frederica?
Yeah, sure. So we have a few questions that have come through. By the way, guys, if you have more questions, then send them through and I'll pick them up now as they come in. But to answer the ones we have, so someone asked on the quickfire questions here, on the third question, they said, if one lamp is burnt out, what will that lamp still have resistance?
No, if the lamp is burnt out, then it just breaks the circuit. So the resistance, it won't have resistance, it's completely broken. It only has resistance if it's working and it's a fully working bulb.
Cool. And then we had quite a few questions asking to go back to the facts on parallel and series circuits at the beginning, and maybe just run through them again.
Yeah, so as I said, these are so important for electricity questions. So with parallel circuits, current sum, voltage is the same. So parallel, current, sum, and voltage, same. So current sums, voltage, same. And in series circuits, voltage sum and current same. Okay. So they're the facts again. So in series, it's also important to remember about resistance. So we don't need to worry about resistance for parallel, but in series, we do need to worry about resistance. So the resistance is just sum. If we have two resistors in series, they just add up together to get the total resistance in the circuit. And that's however many components we have. So you might be a little bit confused about resistances and components. So these squares are just plain old resistors. These squares here, or rectangles, sorry, are just plain old resistors. Okay. Now we also have variable resistors. So you might have seen this circuit symbol, and they are ones where the resistance can be changed. A plain rectangle is a fixed resistor. Okay, so fixed resistor, changing resistor. And you might use these in labs. It's kind of a thing that you slide across. And then we also have bulbs. Now, remember that bulbs also have resistance. So they are there as a light source, but because of their nature, they have an inherent resistance. So they have a resistance associated with them. Okay, so bulbs are not just a light source, they're also a form of resistance. We don't tend to use them for resistance, but it just kind of comes along with the fact that they are a bulb. Okay, so that's the facts for parallel. I sum, V same. Current, V sum, I same.
Cool, thank you. Another question that's sort of related to that was, is there an easy way for remembering the rules for those two different types of circuits?
Well, obviously everyone has their different kind of ways of remembering, but I just remember I sum and I same. So I sum, I same is kind of like a bit catchy, I don't know, if you want to remember it like that. So I sum for parallel and I same for series. And then you can just kind of work out the other one from that. If you just remember I sum, then you know that V must be same. And if you remember I same, then you know that V must be sum. So that's kind of how I remember them. So parallel, I sum, series, I same.
Cool. And then we had a question saying, can you please go through one more quick fire question?
Absolutely. So let's go through the next one. Okay, so we have, let's do this one. So 3 identical lamps are connected in series to each other. So we're doing this one here. 3 identical lamps are connected in series to each other and then connected to a 6-volt battery. What is the voltage drop across each lamp? So it's kind of like one we've already had. So the eager-eyed of you will notice that. Now there are 3 identical lamps. So remember that the voltage drop in series is sum. So the voltage drop across each lamp is 2. And that one was our quicker one. So let's just do the last one here. 3 1.2 ohm lamps are connected in series. So here, they're not resistors, they're lamps, but because they are lamps, they have a resistance. So we have 3 1.2 ohm lamps. So 3 1.2 ohm lamps connected in series. And if you're getting confused, bulbs are the same as lamps. And they look like this with their circuit symbols. So we have 3 lamps. They each have 1.2 ohms and they're connected to a 3-volt battery. So if we have 1.2 ohms and 1.2 ohms and 1.2 ohms, well, we're in a series circuit. So the resistances add. And if we add 1.2, add 1.2, add 1.2, we get 3.6. So 3.6 is our total resistance in the circuit. And then we use V equals IR, where we have V is 3. We're trying to find current. And we have R is 3.6. So that's not a 1, that's I. And then if we divide both sides by 3.6, we get I equals to 3 divided by 3.6. So you should be getting 0.83 recurring. And obviously you would put it to however many significant figures the question asks for, like that. So it's perfectly acceptable for you to just write 0.83. And then the last question here is, how does the current behave in a series circuit? Well, we know that current is the same in a series circuit through all the components.
Cool. Okay, so with the couple of minutes we have left, maybe we should just do one final question.
Yeah, absolutely. So this is actually an extension, so it's kind of a good question to end with. So we've only been talking about resistors in series today. So now we're going to move on to resistors in parallel. So it's just another equation that governs resistors in parallel. So here we can see that these two resistors are in series, but these two resistors are in parallel. So now we have a mixed up circuit of a bit of series and a bit of parallel. Now we have a different rule for resistors in parallel, and it's this rule up here. 1 over the total resistance equals 1 over each resistance in turn. So let's call this resistance 3 and this resistance 6. So ignoring the rest of the circuit, let's just deal with the resistors in parallel. So we're just dealing with this part of the circuit here. Don't worry about all of this over here. We're just dealing with this branches of the circuit now. So 1 over the total resistance, which is what we're trying to find, equals 1 over resistance 3 plus 1 over the other resistance, which is 6. Okay, so we do 1 over one of the resistors plus 1 over the other resistor. So that's 1/3 plus 1/6. Which is 1/2. And that equals 1 over RT. Now you might be able to see it already, but we can cross multiply. So we cross multiply this side and we get 2, and cross multiply the other side and we get RT. So the total resistance in this part of the circuit, this black square, these parallel branches, is 2 ohms. So RT here is 2 ohms, but that's not the total resistance of the circuit. That's only the resistance of these parallel branches. So 3 and 6 are just the values of resistor 3 and resistor 4. We do 1 over the value of one resistor plus 1 over the value of the other resistor equals 1 over RT. Now, a common mistake that we tend to make in parallel resistors is leaving RT as 1/2. But we have to remember to flip it over so that we get 2 over 1 and resistance is 2. If the numbers aren't that easy, then you will definitely have a calculator in the exam. So don't worry, you just plug it all into the calculator, do 1 over the answer, and you should get the total resistance. Now, that total resistance turns into one single resistor. So now we have a circuit diagram that looks like this. Okay, so I'll just repeat that. These two resistors here, resistor 3 and resistor 4, can turn into one single resistor, okay? Obviously not physically, that doesn't happen, but when we're doing calculations, we can pretend that these two resistors turn into one resistor of 2 ohms, okay? So that's now a 2 ohm resistor. So we've used the calculation of the total resistance in these two branches to turn it into one resistor. The reason we do that is just because it's much easier to work with. And now we should be able to find the total resistance of the circuit. So this circuit turns into this circuit, which is now a series circuit. So we've turned a compound circuit, which is a mixture of series and parallel, into just a series. So if I give you the values of resistor 1 and resistor 2, 5 and 4 respectively, could you tell me what the total resistance of our new circuit is? So we have one resistor as 5, one resistor as 4, and one resistor as 2. So if we add up all of our resistances in series, because we can see this is a series circuit, we should be getting 11 ohms for the total resistance. So just to go over that, first of all, we saw that we have 2 resistors in parallel. One resistor was 3 ohms and one resistor was 6 ohms. So we first of all need to find out the resistance in this part of the circuit, this parallel part of the circuit. We use this equation here, which is 1 over the total resistance equals 1 over the value of one resistor plus 1 over the value of the other resistor. We add them up and we get a single fraction. That is equal to 1 over RT, not RC, remember. And then we can do 1 divided by this answer, cross multiply, or just by inspection. However you want to solve this equation here to get our final value for RT. RT is 2. Then we turn it into 1 resistor of resistance 2. So we change this parallel part of the circuit into just 1 resistor, which can now be in series with our other 2 resistors as a 2 ohm resistor from here. And then we can add up resistances in series, which we know just sum together to get 5 plus 4 plus 2 is 11 ohms.
Perfect. Thank you so much, Prashayla, and thank you everyone else for coming to the live group tutorial today. Just a few things to answer before we finish up. So all live group tutorials are an hour long and they will be recorded. So a lot of you have been asking if you'll be able to watch stuff back. You will be. We send out links to all the tutorials so you can watch them afterwards. We'll also be able to share the PowerPoint that Prashayla used today, because I know that lots of you found that really useful. A lot of questions have come in asking how often we're going to have tutorials. So all I can say is look out for a schedule from us shortly that will let you know what subjects to expect on what days. I'm also going to be sharing a link to a survey which I've just done now in the chat. So if you fill out the survey, you can let us know how you found today's session, and then we can go from there to make them as engaging and as interactive as we can for everyone. That's it from me, and hope to see you guys shortly in some of our other group tutorials that will be happening soon. Thanks everyone, have a good day.
Thank
Bye.
you.